Good morning. Today I am going to give the lecture 2. It is in the continuation of my previous lecture, which was on polymers, and today I am going to discuss the various mechanisms which are related with the addition polymerization. Yesterday we have discussed the classification and we saw that the classification based on various parameters, and among them one of the classification was on the basis of the polymerization. So today we will see that addition polymerization reaction can follow three mechanisms. Out of three mechanisms, the first one is the free radical, number two that is cationic, and number three is a anionic one. Let me start with the free radical polymerization. The free radical polymerization consists of three fundamental steps, that is initiation, propagation and termination. Initiation involves the formation of radicals followed by the radical reaction with a vinyl monomer. Propagation is the rapid and progressive addition of monomers to the growing polymer chain without a change of the active center. The termination is the destruction of the growth active center, usually by combination or coupling of the radicals of two growing polymer chains or by disproportionation. In addition to these three processes, chain transfer might occur, which is the transfer of the growth active site for the active chain to an inactive one, a monomer or a solvent molecule. The initiation step, in the initiation step, you can see that there is a generation of active species, and the free radical can produce in a number of ways, including thermal or photochemical, decomposition of organic peroxides, hyperoxides, azo or diazo compounds. The free radicals which are used are benzoyl peroxides, AIBN, that is isobutyl nitrile, and they are free radical initiators. The following in its generation, the free radical then reacts with a vinyl monomer. Then it adds to one of the electron of the double bond of a vinyl monomer, and the remaining electron becomes the free radical. Thus, the process of chain initiation involves two steps. The first being the decomposition of the initiator to yield a pair of free radicals, and the second, the addition of a monomer to a primary radical to yield the chain radical, which is termed as initiation. In the next, the propagation part. In the propagation, the growth of polymer chain by successive addition of monomers. During propagation, it can be represented as given by these reactions. You can see that they are joining together to form RM2 or RM3. In general, we can say the X number of M are going to associate with R and turn into RMX plus 1. Further, the termination step, the propagation step would theoretically continue until all monomers are consumed. The pairs of radicals also have a tendency to react with each other and thus annihilate their activities. The termination occurs by two processes, either by combination or disproportionation reaction. In the case of combination or coupling, the two growing polymer chains react with each other, forming a single non-reactive polymer chain, and in case of disproportionation, a hydrogen atom is transferred from one radical to other, resulting in two polymers, one with a saturated end and the another with unsaturated end, and each with an initiator fragment. The another mechanism is followed, that is cationic polymerization. The addition of a proton to an alkene linkage gives a carbocationic species, which is a strong electrophile. Such carbocations are highly reactive and quickly react with available nucleophiles. And the process of this polymerization also follows the three steps, that is initiation, then then propagation and termination. And the cationic polymerization of simple alkenes is especially efficient for alkenes which form relatively stable carbocations and which have one double bond terminus of the alkene unsubstituted, as to minimize steric effects in the transition state for the addition reaction. We can see it through the mechanism. As you can see, the formation of carbocation, and then there is a attack which is going to take place, and finally it is going to form a polyisobutene. The next mechanism which is followed for this addition polymerization is anionic polymerization. Here in this mechanism, the initiator is a nucleophile and the propagating site of reactivity is a carbanion. Only monomers having anion stabilizing substituents such as phenyl, cyano or carbonyl are good substrate for this polymerization technique. Many of the resulting polymers are largely isotactic in configuration and have high degree of crystallinity. In contrast to cationic polymerization, anionic polymerization is relatively efficient when the intermediate anionic species is relatively stabilized. Since alkyl groups are donor groups, simple alkenes are not polymerized efficiently by the anionic method. An example of an alkene which is readily polymerized anionically is methyl acrylate. The intermediate anions are recognized as enolate anions. You can see through this mechanism. Now, let us see some industrially important polymers, their synthesis and final applications. In day-to-day life, we are utilizing many polymers. So we should know that who are such polymers which are industrially important for us. The polystyrene, let us take the first one, that is polystyrene. It is prepared by the polymerization of styrene in presence of benzoyl peroxide as initiator. It is a addition polymerization, and the process, the styrene monomer reacts by free radical mechanism, and we are able to see the polystyrene. The properties of this polystyrenes are they are transparent, high refractive index which give it high brilliance. They are having low heat distortion temperatures, and hence articles made of it cannot be sterilized with steam. Chemically inert, resistant to most alkalis, acids, oxidizing and reducing agents, susceptible to photooxidative degradation which results in brittleness and yellowing. Excellent moisture resistant, and they have good electrical insulating properties. The uses, they are widely manufactured. They are widely used for the manufacturing of articles such as jars, lids, bottles, combs, etc. They are used for preparing synthetic ion exchange resins in the combination with paravinyl dibenzene, used in the preparation of foam and bead for insulation and packing materials. They are high impact polystyrene produced by the combination of polystyrene with butadiene, contributes to improved impact properties and is used for door liners and inner liners of the refrigerators. The next, let us see, that is polyvinyl chloride. This polyvinyl chloride is produced by polymerization of the monomer vinyl chloride by heating its water emulsion in presence of a small amount of benzoyl peroxide. It is also an addition polymer. The vinyl chloride follows the free radical polymerization, converts itself in polyvinyl chloride. The properties, they are colorless, odorless, and non-inflammable. They are resistant to atmospheric oxygen, inorganic acids, and alkalis. The greater abrasion and flex resistance compared to leather. They are waterproof and washable, less brittle and lighter when they are compared to the glass. Uses, they are used as sheets for tank linings, safety helmets, mud guards. They are used for making window frames because it is corrosion resistant. Used for storing edible oils, fruits, squash, etc. They are used for making ladies' handbags, bathroom curtains, kitchen upholstery. Next is PTFE, that is polytetrafluoroethylene, commonly known as Teflon. It is prepared by the polymerization of tetrafluoroethylene under high pressure in the presence of benzoyl peroxide as catalyst. Again, it is a free radical polymerization, and the tetrafluoroethylene, when it polymerizes, converts itself in polytetrafluoroethylene. The properties, they are highly regular structure and highly crystalline in nature. Due to the presence of highly electronegative fluorine atoms, there is a very strong attractive forces between the different chains, which makes it extreme tough. The high softening temperature is 327 degrees centigrade. They are extremely resistant to strong alkalis and acids. Highly dense polymer, therefore have excellent mechanical properties, excellent insulating properties. They are used as non-stick coating for pots and pans, used as an insulating material for transformers, cable, wires, fittings, etc. Suitable material for making gaskets and seals. Due to its extreme inertness and high temperature stability, they are used in non-lubricating bearings. The next is low density polyethylene and high density polyethylene. The general synthesis of the polyethylene, when the ethene reacts when the ethene reacts by addition polymerization, converts itself in the polyethylene. The difference, the low density polyethylene, it is a branch chain structure, whereas the high density polyethylene, it's a linear structure. Let us first see low density polyethylene. Low density polyethylene is a semi-rigid and translucent polymer. If we compare to HDP, it has a high degree of short and long chain branching. It is produced at high pressure via free radical polymerization process. LDP having a melting point of 105 to 115 degrees centigrade. The density of LDP is 0.91 grams per centimeter cube. Chemical resistance of LDP is towards alcohol, dilute alkalis, acids. They are having limited resistance to aliphatic and aromatic hydrocarbons, mineral oils, oxidizing agents, and halogenated hydrocarbons. They are temperature resistant up to 80 degrees centigrade continuously and 95 degree for shorter times. Low cost polymer with good processability, high impact strength at low temperature, good weatherability. They are excellent electrical insulating properties, very low water absorption, transparent in thin film form. HDP, that is high density polyethylene, it is cost effective thermoplastic with linear structure and no or low degree of branching. It is manufactured at low temperature and pressure. High density polyethylene melting point is between 120 to 140 degrees centigrade. The density of HDP lies between 0.93 to 0.97 grams per centimeter cube. High density polyethylene chemical resistance. They are excellent resistant to most solvents. They are resistant towards alcohols, dilute acids and alkalis. Moderate resistant towards oil and greases. Poor resistant to hydrocarbons. Continuous temperature is minus 50 degree to plus 60 degree centigrade. They are relatively stiff material with useful temperature capabilities. Higher tensile strength compared to other forms of polyethylene. They are good low temperature resistant and very low water absorption. The next polymer is PMMA, that is polymethyl methyl acrylate. It is routinely produced by emulsion polymerization, solution polymerization, or bulk polymerization. Generally, radical initiation is used, including living polymerization method, but anionic polymerization of PMMA can also be performed. PMMA produced by radical polymerization, which is atactic, and completely amorphous in nature. Methyl, when methamethyl acrylate, in the presence of benzoyl peroxide at 393 Kelvin reacts, it turns into polymethyl methyl acrylate. The properties of polymethyl methyl acrylate: they are highly resistant to UV light and weathering. They are excellent light transmission, unlimited coloring options. They are having excellent transmittance. Their surface is very hard, tough, durable, and lightweight thermoplastic. Chemical resistant. It is unaffected by aqueous solutions and detergents, cleaners, dilute inorganic acids, alkalis, and aliphatic hydrocarbons. Their end application finds in for designing LED lights, where it helps maximize light emitting potential. It is also used for construction of lamps thanks to its transparency and optical properties. Next, it is used in automotive and transportation purposes. In vehicles, PMMA sheets are used in car windows, motorcycle windshields, interior and exterior panels, fenders, etc. Also, the colored acrylic sheets are used in car indicator lights, covers, interior light covers, etc. They are also used for window of a ship and aviation purposes. PMMA also open new design possibility for car manufacturers thanks to its pleasant acoustic properties, outstanding formability, and excellent surface hardness. Next, that is polycarbonate. The polycarbonate, it can be synthesized by interaction of sodium salt of bisphenol A with phosgene. In the presence of phosgene, they are converted in polycarbonates. The properties: they are totally amorphous polymer. They are having high impact strength. They are resistant towards water and high melting point, that is 265 degrees centigrade. They are also having high transmittance and good electrical insulation characteristics. The uses of polycarbonates: they are used for making the molding for computers, calculating machines, compact disc, etc. They are used for making laminated bullet resistant glass, used for making microwave cookware, transparent baby bottles. They are used to make shatterproof windows, lightweight eyeglass lenses. Next is polyethylene terephthalate, which is synthesized by the reaction between terephthalic acid and ethylene glycol, which converts itself into polyterethylene convert into poly, or you can say PET, polyethylene terephthalate or PET. The properties: they are crystal clear polymers, they are pure, they are safe to use, they are good barriers, light in weight, recyclable, and good resistance power. Their usage: they are used for manufacturing of shopping bags, water bottles, videotapes. They are used for manufacturing of containers and bags, used to manufacturing of clothes and housing material, water bottles, microwave containers, carpets, and packaging films. With this, I will stop my lecture. In the next lecture, we will continue with some industrially important polymers. Thank you so much.